So welcome to this next lecture. In the last class, what we have seen is how a well-mixed reactor and a plug flow reactor, how they respond. We saw two ways. One was a pulse injection and one was a step change, and how the E curve, how the F curve can be used to decipher how these reactors respond to a step change of tracer. And we've also seen an example that a real life reactor, how we can calculate the RTD E curve of that reactor, and we have seen that they behave totally differently. And we just at the end of the last lecture we talked about different things. One is small deviation, or maybe well mixed tanks in series, small deviation from plug flow, dispersed plug flow model, and third thing that we see is compartment model. These are the three things that we are going to see. How do we use them to characterize a real life reactor, and then we'll go forward as to how to calculate conversion and all those things. Just to get you started, this is where we are in the course. We are on third topic, and just to get you to revise of the previous lecture so that you are in a better shape to understand what is going to come in this lecture, I want you to write an expression for ET in terms of C out at time t. What is the physical significance of ET? What is the relationship between E theta and theta for well mixed behavior? What is the relationship between sigma theta square and sigma square and tau? What are the characteristics of a good tracer? Okay. Right, let's go forward. So this is what we are going to do. This was there in the last class. We are going to look at one, series of well mixed tanks, two, dispersed plug flow model, and three, compartment model. These are the three ways in which we characterize or we quantify how a real reactor behaves as a combination of some idealized reactors, and then we'll use it for some purposes. This is what we are going to do. So we are going to, in this lecture, we are going to look at series of well mixed tanks and dispersed plug flow model, and then we'll do some problems based on that. In the next class we will do compartment models. Okay. So when we say series of tanks, we are saying that each tank behaves like a well mixed tank, and then if I put a pulse of tracer here, how the response is at the outlet. So a real reactor, we are saying a real reactor would be here, and this real reactor is behaving as a, so our real reactor may have one stirrer, two stirrers, whatever it may be. And so how this real reactor is behaving, one possibility is it is behaving like series of well mixed tanks. So I would like you to derive an expression, derive an equation for, let's rub this one now. I would like you to derive an expression for the E curve, ET, sigma square, E theta, sigma theta square in terms of residence time tau I in each well mixed tank. So when I say a real reactor is behaving like a series of well mixed tanks, there are two parameters which are characterized. One is tau I, the residence time in one well mixed reactor or one well mixed vessel. I should not simply say reactor. And n, number of well mixed vessels in series. These are the two things that will characterize how this system behaves. Okay, so derive equation based on the pulse of tracer that we had put in. Derive it for yourself. Okay, so here is the derivation. If you think of two tanks in series, I have put a tracer, we have put a pulse of tracer here, right, at t equal to 0, and we want to see how the outlet concentration changes with respect to time at the outlet of the second reactor, two tanks in series. So if you write that for the first tank, you will get d Vc1 by dt is equal to minus Fc1. That you can write C1 at time t would be C at time t equal to 0 e raised to minus t by tau I. Tau I is the residence time of one tank. Same balance we can write now for the second reactor. We'll get V dC2 by dt is Fc1 minus Fc2. Then we'll have to solve this equation and get C2. From this equation we will have to get C2 as a function of time. From there we will get the E curve at the outlet of the second reactor. Okay, or if you are doing 3 tanks in series, this is the equation for first tank, this is the equation for the second tank, same way you will get an equation for the third tank. Okay, then this equation when I solve, I will get C3 as a function of time. From here we will get the E curve for a series of 3 well mixed tanks in series. Remember, each one there is a residence time tau I, residence time tau I, residence time tau I, residence time tau I, residence time tau I. In general, tau I dCn by dt. So if you look at all these things and simplify, this is what you will get. This equation is what you will get. And n can be 3, 4, 5, 6, 7, whatever number we want, right? This is the generalized expression for the mass balance of the tracer for nth reactor or nth reactor. N can be 1, you will get this. N can be 2, you will get this. N can be 3, you will get this. Okay. So you can solve for yourself. I'm just going to generalize. I'm just going to give you a answer. Here is the residence time distribution E curve for n tanks in series. So it will be t raised to n minus 1. N minus 1 factorial tau I raised to n e raised to minus t by tau I. Remember, tau I is residence time for each well mixed vessel. Now we are going to say reactor, but we can use this methodology to analyze any equipment. It could be a dryer, whether we want to know whether the dryer behaves like a plug flow or well mixed. It could be a absorption column. It could be a distillation column. It could be anything, right? Okay. In terms of theta, if you want to write, E theta would be n raised to n, theta raised to n minus 1 divided by n minus 1 factorial e raised to minus n theta. So derive this for yourself. Homework is derive this. Sigma square will be n tau I square, tau total square divided by n. Okay, or sigma theta square is 1 by n. So derive all these equations for yourself. Okay. Derive all these things for yourself. So what I want you to do is use this data in the previous problem. This was our reactor that we had said. We have done an RTD study on a real life reactor. This is the behavior that we get. I would like you to fit tanks in series model to this data. Okay. Just remember, this experimental data we have characterized by these parameters. Experimentally we have calculated all these. Okay. So use a spreadsheet software to do the fitting. Two important points come into picture. How do I decide whether the fit is good or bad? Okay. What we will need to do is, that's the first thing, and second is, how do I define error? So whether fit is good or not, we define by an error between the predicted value of E curve predicted using a tanks in series model. This is the prediction and experimental ET, and then we try to minimize the error. That's what we mean by fitting. We are going to fit tanks in series model. So when I say tanks, it is well mixed tanks, right? So what we are going to do is we are going to use E curve for tanks in series model, calculate this error and minimize that error with respect to the parameters in the model. What are the parameters in the model? Number of tanks in series and residence time for each tank. Okay, do this for yourself. Okay, then only go forward. Pause the video. Unless you do it for yourself, don't go forward. Pause. Okay, here is the analysis. First of all, our experimental data, we have got sigma theta square is 0.19. So 1 sigma theta square, recall, for tanks in series is 1 by n. That means our sigma theta square is 1 by n equal to 0.19. That means n is equal to 5.26. That means our experimental RTD is already telling us that this is going to behave like 5 tanks in series or like 6 tanks in series. You can't have a fraction tank in series, right? It is either 5 tanks in series or 6 tanks in series. Second thing it is telling you is sigma square. Sigma square was 36.85 and tau was 13.91. And look at sigma square. Sigma square is tau total square divided by n. Okay, or sigma square is n tau I square. So 36.85 would be n tau I square. So if I take n is equal to 5, I will get a value of tau I. If I take n is equal to 6, I will get approximately another value of tau I, right? So our values, experimentally observed values, are already telling us that this is going to behave like 5 tanks in series or 6 tanks in series. Each tank is going to have a residence time of 2.65 approximately. These are approximate values because we have not fitted yet. It's only global parameters of sigma theta square, sigma square, tau is what is telling us that this is how it is going to behave. This is approximately how it is going to look like. But it is still necessary to fit values of n and tau I to observe data. So what I want you to do is take different values of n. Say for example, take n equal to 4. Take some value of tau I. Okay. What will you take? From here maybe. Right? Take some value right now. So take some value. Maybe see if n is equal to 4, this will be like 9. Tau I would be approximately 3. Let's say. Take tau I equal to 3. Calculate E curve ET versus T from, let's say, 4 tanks in series and tau I equal to 3. You will get a curve. You will get a E curve prediction. Compare this with experimental data. Experimental, actual ET. Okay. Now we have to vary these parameters. So we have to vary n, we have to vary tau I, so that the predicted behavior matches the experimental behavior, actual behavior, or the error is minimized. That's what we mean by fitting. Okay. So what I will request you to do is take n equal to 4, vary this tau I, so that we get a error. And error we are defining in terms of root mean square error. Get a value of error. Try to minimize the error by varying this tau I. Okay, then you will get some value of error. Then take n equal to 5. Take tau I equal to some value, say 2.7. Calculate the error. Calculate RMSE. Minimize RMSE. By changing tau I, this value now. Okay, you will get a minimized error. Take n equal to 6, take n equal to 7. Each time you will get a value of tau I which minimizes the error. Now you can see whether this error with 4 tanks, with 5 tanks, 6 tanks, 7 tanks, which of these errors is lower. Okay, or you can use some optimization, minimization software. Even a spreadsheet like Excel has that. But do this yourself. Okay, do this yourself. Pause, then only go forward. Pause, and do it for yourself. So here is the answer, or here is what you will probably get. Maybe if you've done things properly. So this is your experimental actual E curve, actual time versus ET. Now we can take n equal to 3, let's say tau equal to 4.9, predicted sigma would be 72, predicted sigma square would be 72. Why? Because it is n tau I square, n tau I square. See this? N tau I square. 4.9 square into 3, 72. Error, you can calculate predicted ET using this expression. Predicted ET using this expression. This expression. Now you are going to take n equal to 3, tau I equal to say 4.9 and calculate E from this expression. These are the values that are here. Now we want to find error between this value and this value, between this value, this value, this value, this value, this value, this value, squares that and sum and take square root. Root means square error. It's 3.09 into 10 raised to minus 3. Now we have to minimize by changing this tau I. I've already done that, I'm just telling you. Take n equal to 4. Again, calculate using this formula. Now n equal to 4. Say tau I is equal to 3. Calculate using this formula. Okay. These are the predicted values. Minimize the error between this value and this value, between this and this and this. Okay. These are the sum of the squares of the error. Minimize that. Minimize this error by varying this tau I. Same way do for 5 tanks, 6 tanks, 7 tanks, and you will compare these different errors now. This is 3.09 into 10 raised to minus 3, 2 into 10 raised to minus 3, 1.39 into 10 raised to minus 3, 1.39 into 10 raised to minus 3, 1.78 into 10 raised to minus 3. So these two models behave nicely. Behave nicely means they are fitting the actual RTD behavior. Okay. So if you plot graphically, this is a summary. 3 tanks, 4 tanks, 5 tanks, 6 tanks, 7 tanks in series. Root mean square error for each of them. You see, root mean square error is lowest for these cases. This is the fitted value for each case. You can compare graphically now. This is red line is for 4 tanks. Blue line is for 5 tanks. This orange line is for 6 tanks, and this green line is for 7 tanks. Okay. Compare with these experimental values. These are the experimental values. Which one do you think fits nicely? 5, 6? Right? They're all the same. 5 and 6 is practically the same. You can take approximately 6. This is a good fit. In terms of sigma theta square or sigma square, 37.26 is closer than 31. So we can take 5 tanks in series as a good fit to this real reactor. Now you see how we can find out that this actual reactor, which had this observed tracer response, behaves like 5 tanks in series, each tank having a residence time of 2.73 minutes. Okay. Although in terms of mean residence time, 13.68 is closer to 13.91. But in terms of dispersion, 37.26 is closer to 36.85 than 31.9. So we are saying that this is a better fit. Spread is better predicted. Residence time practically no difference. Whereas 3 tanks in series, residence time also is bad. This is also bad. 7 tanks, this is okay. This is not okay. You see, prediction is okay here, but prediction is very high here for 7 tanks. So this is how we would fit a tanks in series model. So that takes care of first category. First category is well mixed tanks in series. Right. Let's go to the second category, dispersed plug flow model. Plug flow with dispersion. Okay. So when we say plug flow with dispersion, what we mean is that there is going to be axial mixing. Axial mixing. So this axial mixing, what is going to do is, if I put a pulse of tracer, axial mixing, this tracer pulse is going to mix with fluid which is ahead. This tracer is also going to mix with the fluid which is behind. And gradually this tracer pulse would broaden because of mixing. And because it broadens, the concentration inside this tracer pulse is going to reduce. So if you put a pulse of tracer like this at the start of the reactor or start of the vessel, after some distance, it is going to spread. It is not going to be like pulse, it has spread, as well as the peak has reduced. After some more distance, it has spread even more. The peak has reduced. After some more distance, the peak has reduced and it has spread even more. So how it spreads and how the peak decays tells us what is the extent of dispersion in this vessel, in this reactor, if you like. So now if you write one dimensional version of this, we will say del Ca by del T plus Vz. Now flow is only in the Z direction. So Vz del Ca by del Z dt del square Ca by del Z square, because we have said in the radial direction it is very, very fast. But axial direction now it is comparable. Dispersion and convection are comparable. Okay. So what we'll have to do is solve this equation so that, and vary the value of dispersion coefficient, so that the peak, the concentration as a function of time that is predicted at the outlet matches my experimental data. What is the experimental data? This is the actual experimental data on an reactor. So we are going to vary now the dispersion coefficient so that the predicted outlet concentration of the tracer, not the reactant now, the tracer, matches our experimentally observed value. Okay, so that means I have to solve this equation. How do I solve? So there are a couple of things before we solve. First of all, something to do with our dispersion coefficient. Something to do about dispersion coefficient. So dispersion coefficient in pipelines, several correlations are there. One of the correlation is turbulent dispersion coefficient is 5.05 into diameter into V star. V star is like friction velocity. Friction velocity is root F by 2 into the average velocity. Remember your universal velocity profile you might have studied in your undergraduate course. V star friction velocity is root F by 2 into average velocity. That's what we have put here. That is one correlation. Second correlation is turbulent dispersion coefficient divided by dV. This is like turbulent Reynolds number, if you like, is equal to 3 into 10 raised to 7 Re actual Reynolds number in the pipe raised to 2.1 plus 1.35 Re raised to 0.125. You can plot all that for yourself, but that's not important. What we will do is, and this is how the dispersion coefficient looks like in, let's say, packed beds. So Reynolds number in packed bed versus dispersion coefficient in the packed bed. This is the data for gases for different values of Schmidt number. Schmidt number 0.2, Schmidt number 0.35, Schmidt number 1. and this is the data how it looks like for liquids. This is all experimental data. This is experimentally measured dispersion coefficient. How do you measure experimentally? Is do a pulse injection and vary this dispersion coefficient to match experimental observations. Okay, this is for packed beds. This is for pipes. Okay, just to give you an example, just to make you calculate and understand how all these things are calculated. So let's calculate the dispersion coefficient in a pipe 50 millimeter in diameter, 25 meter long, and a water flow rate of 10 meter cube per hour through the pipe. Molecular diffusivity in water is 10 raised to minus 9 meter square per second, and also calculate the Peclet number. So solution, if you want, it's already there, you don't have to do it, but do it for yourself. Average velocity would be 10 meter cube per hour divided by 3600, that will give you meter cube per second, divided by cross sectional area. Cross sectional area would be pi by 4 multiplied by diameter 50 millimeters, so 0.05 meters, 5 centimeters, 0.05 meters square. This will be cross sectional area in meter square. This will give you velocity in meters per second. This is the average velocity. So what is the Reynolds number? It is d 0.05, velocity 1.41 into rho 1000 divided by mu 0.001, 70,500 if you like. If flow is highly turbulent, then at this high RE, one is we can use the graph. Look at this graph. RE is 7 into 10 raised to 1, 2, 3, 4. 7 into 10 raised to 4. RE is 7 into 10 raised to 4. Look at this graph. 7. This is 10 raised to 4, 10 raised to 5, 10 raised to 7 into 10 raised to 4 would be somewhere here. Turbulent diffusivity divided by turbulent dispersion coefficient divided by dV would be around 0.22. Use that. So dt would be 0.22 multiplied by velocity multiplied by diameter. You will get dispersion coefficient as 0.0155 meter square per second. Peclet number would be VL divided by dt, 1.41 into L, 25 meter long, divided by dt, 0.0155, 2274. Is it far greater than 1? Yes. Flow is very close to plug flow. Okay. Or if you want to use a correlation, use some correlation. Let's say this correlation, right? This correlation if I want to use. So dt by dv would be 3 into 10 raised to 7 divided by re raised to 2.1. What is re? 7 into 10 raised to 4 raised to 2.1 and plus 1.35 re raised to 0.125. re means 7 into 10 raised to 4 raised to 0.125. This will be dt by dv, and then multiply by d multiplied by v, you will get dispersion coefficient. You will get this value. Peclet number would be VL by dispersion coefficient. Either you can take this or you take this value, whichever one. Oh, sorry, this is actually it cannot be 0.0155, it has to be 0.024. Wait, let me just make that correction. So I made that correction now. Yeah, it is 1.41 into 0.25 into 25 divided by 0.024. That's what we have used from the correlation. You get 1469. Okay, far greater than 1, very close to plug flow. Okay. So now if you have to solve, we have to do couple of things. One is, if dispersion coefficient is small, d by ul is 0.01, that means Peclet number is greater than 100, then the spread of this tracer as it spreads more and the peak reduces, this spread will be symmetric. Why? Because the dispersion coefficient is small, Peclet number is greater than 100. Okay, then we can represent it by a Gaussian curve, Gaussian distribution, and these are the characteristics that are calculated. We don't have to mug up all these things. We are not going to into details of how this comes about, but I'm just going to give you a answer. I'm just going to give you an answer. E theta would be tau E. It will be dispersion number or inverse of Peclet number 1 minus theta square 4 and inverse of Peclet number. In terms of E, actually if you want, it will be square root U cube. U is the average velocity, L minus ut. So you can get these for yourself. You can take this expression and derive this from this expression, right? And this is how the spread will look like. The peak is when theta is 0. When theta is 0, it is e raised to 0, that is 1. So peak E theta would be e raised to 0 is 1. It will be 1 by square root 4 pi divided by Peclet number, or I can bring this Peclet number in the numerator as well. It will be Peclet number divided by 4 pi. This whole thing. Okay. And the spread is related to the dispersion coefficient. See, sigma theta square would be 2 d by ul, or sigma square would be 2 dl by u cube. These are the things that we would be requiring now. If Peclet number is less than 100, that means there is a large dispersion. So then the curve is no longer symmetric. If curve is no longer symmetric, we have to actually solve this equation, the dispersed plug flow model. Now, to solve that, we need boundary conditions. So if this is our vessel, we can define two kinds of boundary condition. One is closed boundary condition, means closed meaning there is no dispersion before the tracer enters the reactor. Closed at the outlet means there is no dispersion after tracer has left the vessel. Open means there is dispersion inside the vessel, inside the reactor, as well as before entering the reactor there is dispersion. Similarly, open condition at the exit means there is dispersion after the tracer has left the exit as well. So this is the condition called as open condition. This is the condition called as closed condition. Or we can have closed open, or we could have open and closed condition. Right? I'm just going to give you some expressions. We are not going to derive. That's not a scope in this lecture. E theta for open, this kind of situation. So most of the time vessels will be open because dispersion can happen before the tracer enters the reactor. Dispersion can happen after tracer has left the reactor. So E theta open would be given by this expression. Actually what you can do is you can take this expression and derive this expression for yourself. You can take any one of them, derive the other. One is in terms of time, one is in terms of theta. And tau for the open case is V by U. V means this is volume divided by flow rate. F is what we have been using. 1 plus 2 by Peclet number. Sigma theta square is 2 divided by Peclet number plus 8 divided by Peclet number square. Right? What I want you to do is fit the data for the dispersed plug flow model from the analysis from this actual reactor. This was the experiment that we had done. This was the RTD for an actual reactor. How the concentration versus time behavior response is for an actual reactor. Okay, I want you to fit dispersed plug flow model to this data. Remember, this data this data has given us or has showed us that tau is 13.91, sigma square is 36.85 and sigma theta square is 0.19. Okay. Which one will you fit? Think about that, whether you will fit this behavior or whether you will fit this behavior. Think about that. Think about that. Pause and do it for yourself. Here's the solution. Use a spreadsheet. Okay, how do we decide whether fit is good or not? Again, so plot E theta versus theta. We have already done this. Does this curve look symmetric? Gaussian? No, it does not look Gaussian. If it does not look Gaussian, that means Peclet number is less than 100 or more than 100. Does not look Gaussian. Means Peclet number is looking like it is less than 100. So in other words, if you try to fit this model using open model, that means we should be fitting this model rather than this model. It's no longer symmetric. So you take these expressions. Okay, E theta for open case, what is the value? 1 by square root 4 pi d by ul e raised to 1 minus theta square divided by 4 theta divided by Peclet number. At theta equal to 1, E theta should be nearly 1, right? And then if theta is 1, that means E theta, this is e raised to 0. So e raised to 0 is 1. So E theta would be Peclet number divided by 4 pi. So when you had actually done this, plotted E theta versus theta for the actual reactor, what is the value of E theta at theta equal to 1? E theta at theta equal to 1 is somewhere in between. Somewhere here. Right? This implies that Peclet number is about 12.6 from here, which means Peclet number is less than 100. Okay. Or I mean, we don't have to take this one. This is actually maybe 0.9. Right? Then correspondingly Peclet number will get. In any case, Peclet number is less than 100. So our assumption that because it is not symmetric, we should be using this model, that's correct. Peclet number is coming out to be 12. It's not going to be coming out to be. It's not coming out to be very large. Or if you like, experimentally, sigma theta square was 0.19. Sigma theta square was 0.19. This 0.19, if I use the model for this model, what is the value of sigma theta square? It is 2 divided by Peclet number plus 8 divided by Peclet number square. From this also we can get Peclet number. So Peclet number is going to be 13.58. Definitely it is going to be less than 100. Right? So what I am trying to say is, now we know approximately range of Peclet number. Peclet is going to be around 10, 12, 13, 15, 16, 20 of that order. So what I want you to do is plot this data, plot this E theta versus theta for different values of Peclet number. Okay, and see what value of Peclet number gives you best fit. Okay, gives you best fit. If you do that, you can do that in Excel, use a solver function or use a error minimization, whatever function you would like to use. You can find that this is what you will get as a fit. These are the experimental values of E theta versus theta. This is the predicted value of E theta for Peclet number equal to 8.34. At that condition, you get a minimum error. Now tell me, this is fitted model. This is fitted dispersed plug flow. Here in this case we have well mixed tanks in series. Now tell me which fit is better. Is this fit good, or slide 11, or is this fit good? Slide 20. Obviously the tanks in series model fits better. RMSE is 0.0014 for 5 tanks, whereas in this case RMS error is 0.0679. Error is several times larger, 50 times larger. Okay, so this is how we would try to fit a model. Let's take one more problem. Here is one problem. There is a tracer, slug of tracer is injected. Slug means pulse of tracer is injected in a long straight pipe. At point A, the spread of the tracer is 16 meters. At point B, 1 kilometer downstream of A, the spread is 32 meters. What would be your estimate of spread at point C, which is 2 kilometers downstream from point A? Okay, do this problem for yourself. Pause and solve. Okay, here's the answer. This is what I'm asking. This is the picture. We have put in a pulse at some point A. Tracer has spread a little bit. This spread I have told you. After some more distance, 1 kilometer, I have told you the spread. I'm asking you what will be the spread here after another kilometer. Right? This is what I'm asking you. If you have not done, pause and do it for yourself. Here's the answer. So let's draw a picture to visualize. Right? I put a tracer after some distance. After some distance, it has spread a little bit. After some more distance, it has spread even more. After some more distance, I am asking you what will be the spread at C. So A, distance between the injection point and A, what is it that we have? At point A, well, we don't know what is the distance. At A, we know that the spread is 16 meters. At B, spread is 32 meters. I want to know spread at C. What we do know is length between A and B we know. This is 1 kilometer. Between B and C, we know it is 1 kilometer. Total A to C is 2 kilometers. We don't know how far behind the tracer has originated. So let's put some distance, LA, as the distance between the injection of the tracer and point A. LB as the distance between injection point of tracer and B. LC as the distance between injection point and C. Now with this visualization, can you solve? Pause, solve for yourself. Okay. So at location A, spread is 16 meters. At location B, spread is 32 meters. If we consider Peclet number is 100, more than 100, because pipeline is very long. So now E theta would be this given by this expression, Gaussian expression. Sigma theta square would be this, or sigma square would be 2 dl by u cube. Now the spread at A is 16, means sigma spread is 16. Sigma at A is 16, sigma at B is 32. So sigma square at A is 256, sigma square at B is 1024, 32 square, 16 square, 256. So now we need to find out sigma C. Okay. Do this for yourself now with this explanation. Pause, solve it for yourself. Only then all these calculations will be clear. Don't see it as if it just for the purpose of seeing. Unless you solve, you will not be able to understand. Okay, so now what are we saying? Because of this, sigma square is going to be proportional to L. right? So sigma square B divided by sigma square A would be LB by LA. So 1024 divided by 256 would be LB. LB, what is LB? LB is distance from the injection point to point B, which is the same. So LB we can write as LA plus distance between A and B, which is 1000 meters, 1 kilometer. LB is LA plus 1000. LA is here. So this gives us LA. LA will get us 333.33. That means injection point is 333 meters previous to A, upstream of A. Now sigma square C divided by sigma square A, sigma square C divided by sigma square A would be LC by LA. LC is LA plus 2 kilometers, 2000 meters, L divided by LA. So this is 2333 divided by 333.33. Sigma square C would be 1792. So the spread at C would be square root of 1792, which is 42.33 meters. Okay. Why these things are important? Why these things are important? Couple of examples let me give you. One is sometimes pipes are let's say in say crude oil storage, or let's say a refinery or a crude oil processing terminal. Same pipeline is used to transport different materials. So sometimes it is transporting diesel, sometimes it is transporting petrol, sometimes it is transporting, let's say, naphtha, something like that. So when, let's say, diesel has traveled, now I want to pass through the same pipeline petrol. Now turbulence will happen and there will be a region. So maybe let's say there is a diesel going here, there is a petrol going here, there is a mixed region which will have properties in between, let's say, diesel and petrol. So this will be off-spec material. It cannot be sold as petrol, it cannot be sold as diesel. This will have to be stored separately and reprocessed to give you properties of petrol or properties of diesel. So that's why this spread is important. How much part we have to take out and how much part we have to reprocess. That's why this pipeline problem is important. That is one possibility. So this happens not just say crude oil, but when you are having same pipeline, you are transporting materials having different properties, and then they mix with each other. So then we need to know how much is the mixed portion, how much is the spread of that material, so that we don't get we remove that material and reprocess, so that we get pure diesel, we get pure petrol. That's one. Second is, let's say there is a river. So imagine instead of this pipeline, imagine that there is a river and somebody has put a pollutant at some location. We want to know how that pollutant is going to persist downstream. How long will it persist? So if you think that this was a river, if you think that this is a river, somebody has put a pollutant here. At this location A, our pollutant has spread this much. So we can advise people that don't go near the river at this point of time. We know how long it's going to take. At this point, we know it has spread more. At this point, we know it has spread more. Concentration has reduced. Okay? So we know that at beyond this point, it is safe now. That it's no longer affecting the aquatic life. It's no longer going to affect the human population, and so on. Those are the things that we can calculate. And more importantly, if I measure, let's say I'm at C, I measure this behavior. If I'm at B, I measure this behavior. I put a probe to measure. Let's say I put a probe here to measure the concentration of the pollutant. As this plug travels, as this spread travels, we will be able to measure concentration as a function of time. We will get it. We will observe it to be. Something like this. Let me just come back. We will observe it to be something like this with respect to time. And then if I measure at two locations downstream of each other, I can back calculate where the tracer would have come from. which industry would have created that pollution. Those are the kind of things that we can calculate from these things, from this expression, dispersed plug flow. These are just two examples I've given you, but there are many others. Okay, so we'll stop here, stop this lecture here. Some problems for you. Fourth edition, if you look at Fogler's book, chapter 14, do problem number 1423. Levenspiegel's book, third edition, the material that we have covered here is in chapter 13-14. You can do problem 13.3, 13.7, 14.5, 14.11. Again, let me emphasize, do the problems yourself, derive equations for yourself, do the fitting yourself. Then only you will be able to understand, and only you will be able to comprehend all the material, and then you will be able to use it for a real life reactor, any reactor that you are going to come across later on in your life. So let's stop this lecture here.